Hi, here we go with the short Chapter 2 summary. Hopefully it'll help you with your review assignment. In this chapter they talk about equations, inequalities, and problem solving, which will get into some word problems and applying algebra to solve word problems. Though when you first start this, it's easy to say, well, you're going to get at word problems that you probably have other techniques to derive an answer to that, which is good, but and a lot of times we will start with things like that to make sure that when you're translating it, you can tell if you got on the wrong path by not being able to solve that problem. And the caution is that then you don't think that algebra is really worth doing. But later on, we'll get into some areas where algebra is probably the only way you're going to be able to solve that word problem. Well, they're going to talk about a lot of terminology like last chapter. There's a lot of terminology, and that's a good place to be, is to get so you know those words and the concepts to focus in on so you can apply these. In this course, as we go on, we're going to apply a lot of these principles and laws, and we're going to go on as if we're not going to reteach all this stuff each time. Well, let's look at this. So we have these sections: solving equations, using principles together, and we'll talk about techniques to solve equations. There's some real hard and fast rules that we'll use, and we're going to look at formulas, which really are equations with multiple variables and so on. And then we're going to get into applications and problem solving inequalities, which we'll talk quickly about. So they'll usually in a book will introduce with some real world stuff that's going on. So the first section is solving equations. I'm just going to hit terminology again. Now, an equation has an equal sign where expressions don't. So we have, these are actually equations and a solution. So a solution is usually something we substitute in for a variable that makes the equation true. Just like this equation here, 8 times 4 equals 32 is true. So this is a true equation. If you didn't have the 8, if that was A times 4 equals 32, we'd say A is equal to 8, so 8 is a solution to this equation because it makes it true. Where like this equation is false, 7 minus 2 is not equal to 4. And then when we have equations with variables, we don't know if they're true or false until we actually start talking about what that variable would be equal to. So in this equation we have x plus 6 equals 13. We don't know if it's true or false. It depends on what value is used for x. Pretty simple concepts, and it's easy to kind of forget it in the mix when we get into more complex things. But that's really algebra, is just simple things built together. It's not more complicated in a sense, like I like to say. It's just more complex, that we're going to take more and more steps as we go on in the course to get to a lot of times when we're looking for a solution. So the key here is to understand what a solution is. It is a value. When I put it into the equation, it makes it true. So both sides are equal. Okay. And then these cautions come up in the book, and I'll point this out probably several times, are usually common errors. It says, note that in example 1 the solution is 7, not 13. We tend to start thinking more in elementary school kind of things where it's what it's equal to. No, a solution is what makes this true. Okay, so there is a difference there. Now, to solve equations, or a short way of saying find the solution to this equation, we get these principles that we can do this. It's kind of like a balance scale, that we can add any number to both sides of the equal sign. It's kind of like a balance scale, if I put 2 pounds more on each side of this thing that's balancing, it'll still balance. So we can basically create equivalent equations, or which are equivalent equations are new equations or different equations that have the same solution. In other words, we can use that as a step model or steps to solve or find solutions to the original equations by creating equivalent equations by following the rules, which in this one first rule is the addition principle. And they show that balance scale again. If we have both these sides are balanced or they're equal weight, if I add the same amount of weight to both sides, they'll still balance or stay equal. And then we're going to have, they go through some examples with that, and then we're going to have deal with subtraction, and which is really adding the opposite. So they don't talk about that really specifically, but the multiplication principle works like the addition principle. They do throw a condition in here, and these are really important issues in here, and you need to get used to this syntax or how they write these things. It says for any real number, though we haven't covered what real numbers are yet, is, which we will in review, but they use these variables a, b, and c, so they have to be only values that are in the real number set, and with c not equal to 0. In other words, the equivalent equation a equals b is equivalent if I multiply the same thing times both sides. But then again, this 0 is an interesting number, because when I multiply by 0, it goes to 0, right? So 0 equals 0, it ends up being a true equation, but it's not necessarily equivalent, or it doesn't help me find a solution. So we got to watch out for zeros, and we also have to watch out for division by zeros. So they apply this principle to create equivalent equations, which is then to find out what the variable is equal to. That's the goal when we go through solving an equation, to find out what number can I substitute in for this variable that will make this equation true. Now again, simple equations, you could probably find solutions in your head just by doing guessing and checking and those kinds of things too. Now here they're showing division, which is really the same, and this is important here, as dividing by -4 is the same as multiplying by -1/4. It's reciprocal, or multiplicative inverse. We'll talk more about that too. Then they bring in this thing, multiplying, dividing by -1. This -1 issue, and I've heard this from a lot of students that, oh, I just get my signs wrong. Well, that is a big deal. We need to really understand opposites. We're going to use opposites or negatives, 1 times something, to our advantage when we're getting into, especially when we're getting into factoring and stuff. So multiplying by any number by -1 changes its sign. In other words, gives you the opposite, and it's kind of pretty kind of obvious kinds of things. But again, when they give us things in the book and put a square around it, those kind of things, it's going to be important, even though it might be a simple idea. We're going to use that quite a bit. Okay, so they go through this, and then what happens when we want to use multiple approaches and stuff like this. This is really something to, this is the next level of hopefully where you get to in these classes, is that you become a problem solver. You can find the best method to find a solution. So like this one, it says to undo the addition of a -8, we could subtract the -8 or add 8 to both sides. I would prefer you stay in addition whenever you can, and stay away from subtraction. The biggest reason is because of the properties involved, the commutative property. If I'm messing around with subtraction or divisions, I got to be real careful about order, because a commutative property doesn't work for those two operations. Okay. So they go through a lot of solving here, and then our exercises here, and I'm kind of taking a little more time on some of these just to point out some things in your book too, and that stuff. And basically what we're going to do then is put both the multiplication principle and the addition principle together. I can rewrite in just more steps equivalent equations with the goal to isolate x or get the variable equal to some number, and then hopefully that is truly the solution. And how would I check that? Well, I can put that possible solution 4 in this case back into the original equation, and that's what they're doing in the check. And does it make it true? Remember what solutions do: make true equations. So is 17 equal to 17? Yes, that's true. So on. So they're using both addition principles, multiplication principles to solve equations. Then they're going to get into something called combining like terms, which is we're going to go through this a lot in especially this course. And really what they're doing is using the distributive property, which we haven't covered too much yet. So they talk about like terms here and stuff, so I'm not going to spend a lot of time there either. But it's a good way to go through and say, hey, how am I going to solve these? These are really strategies that they're going through, clearing fractions. Very good techniques as long as you understand the distributive property. And do those strategies, and here's a box around something, again, good stuff to read about strategies to solve equations. Here's a caution right here: be sure to use the distributive law as used to multiply all the terms by 6. Okay, so if I take 6 times one side, I have to take it times the entire side, so I have to distribute that, and I'd end up with this equation. They're doing this in this case to clear fractions. They're saying, well, if I multiply by the LCM between 3 and 6, which is 6, it'll make all my fractions go away, and I can solve that equation maybe more easily. That's not necessarily the only way to do that. We can add fractions and do all kinds of stuff, staying in fractions, and solve that. But this is a good strategy about being a problem solver again. Same thing here, they're just clearing decimals on that example. Now, types of equations: we have linear equations in one variable. Say x is an equation equivalent to one of the form of ax equals b, where a and b are constants or numbers, and a is not equal to 0. We sometimes refer to these and so on. It's gonna, and really I'm reading this stuff to get used to this language. This language of algebra is trying to be very exact and very necessary for translation from English. So they talk about solution sets, empty sets, identities, contradictions, and conditional equation. And that's defined here. That's something to check out, definitely. So that's section 2, and section 3 of chapter 2 I'm going to get to, and then they get into formulas, which is really just applying stuff like this. So if we have like the energy equals the speed of light, mass times the speed of light squared, those kinds of things, those are formulas. So you're looking at these formulas, they still have like this formula here, P equals 1.2x divided by S, or over S. If we put values into that, we can find out, numbers come out of that. Well, I may not want to find P, in this case, the ticket price. I may want to find out Um, the S in this case, which is they're defining here, is I could solve that for a different variable, and that's what they're talking about here. And this is where circumference of a circle and those kinds of things. And this pi is really a number. It's a real number. 3.14 is an estimate of it, or 22/7 is an estimate. They use this symbol because they've never been able to write it as a rational number or an exact fraction. So depending on what we're going to do, that pi comes from, if you took the circumference of the circle, which is a distance around the circle, and you divided it by the diameter, you always get this special number called pi, which is 3.14 is an estimate for it. Okay. On your calculators, if you hit the pi key, it actually uses a more accurate estimate of pi. It's actually using more digits than are even displayed on your calculator, and so on. But in algebra, a lot of times we do not want an estimate answer. We're going to want an exact answer. But that's not really what they're talking about here. We're going to solve these things. So if I want to find out the circumference of a circle, all I need to know is the radius. I take 2 times pi times whatever radius is, if it's 2, so it'd be 2. I do that calculation, I'm going to get the circumference. Well, if I want to find out what the radius, if I know what the circumference of the circle is, I could solve for r, the radius, by dividing both sides by 2 pi. And I get circumference divided by 2 pi equals the radius. So if I know what the circumference is, I just divide that by 2 times 3.14, or pi, really, if I want to be really exact. Motion we use a lot. This is distance equals this, and really it all generates from this. Rate is really a distance over time. Usually we express rates as distance over 1 unit of time. So like we say that we're going 60 miles in, or divided by 1 hour. That would be 60 miles per hour, and so on. But rates are always this way. It's distance divided by time, and we can change that if we want to find out how long it's going to take to go somewhere. We can redo this formula, say time will equal distance divided by the rate, and so on. More examples, more complicated examples. Here's some cautions about making sure that we don't leave things behind. And remember what our goal is, to get an equivalent equation equal to some specific value. So that's the quick deal. Here's our mid-chapter review, which is not an assignment, but it goes through those first 3 sections. And then they get into percents, and all I'll say is about percents. Percent is another word for hundredths. So if I say 70%, that means 70 over 100. It's just a comparison or a fraction to do that. And I think if you can remember that, instead of memorizing a whole bunch of techniques to deal with percentages, remember that it means hundredths. And you should know how to write 78 hundredths in decimal form. That's 0.78. That's 78 hundredths, okay? They go through a lot of percent deals. There is some translation issue, making sure you can translate them into the right expressions. And with the skills on how to write equivalent equations and solve or find solutions to equations, we use algebra on those percents, which we didn't have in prior math classes a lot of times, so you had to remember if the percent problem's written this way and da 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 da. You had to memorize a lot of stuff. and do that. This problem solving is applying these algebra principles to word problems. So the translation, these are good things to think about. I want to familiarize yourself with the problem. And one of the ways to do this is, I find a lot of students, including myself, is that if I read things out loud, a lot of times when I read them silently to myself, I'm going like, I'm not sure where they're going with this. If I read it out loud, I'm going, oh. And I think that's one of the advantages if you work with other students in your class. You end up talking about this stuff, and that really does enlist a different part of your brain to focus in on what you're trying to find out or get a strategy to solve. Then you translate these expressions and operations. You get looking for keywords for operations like addition, subtraction, multiplication, division, and do that. Then carry out some mathematical manipulation, like solving an equation. Check to see if what answer you think you have. Make sure you go back to the original problem and do this. Here's another box to go through, which is very, very useful steps to go through. Have a lot of problems. A lot of students get in a lot of trouble when we get into these application of this stuff, and that's really what all this section's about. A lot of different types and methods and some other tools. A lot of times, sometimes to draw a picture of anything is always a useful method to do that. And you can think about pictures sometimes, or tables like this. They're going through this problem. They say, well, let's write down what we know and so on, and let's get it in an organized manner, and maybe I'll get some ideas of what I need to do. I guess let's stop at that caution again. Always be sure you answer the original problem completely. I see this a lot. You go through a lot of work. It can take you a lot of time on some of these word problems. Get through all that stuff, be exactly on the right track, and then not answer the question that they're asking in the word problem. So make sure you go back and say, hey, I got 22 what? It might be shots from the court or something like that. And does that make sense? And go back and reread the problem and say, oh, that's not what they're looking for. They're looking for something else. I have this probably in my work right now. I just need to make sure I answer the question. So on, and they go through the pictures and going through these steps that they've introduced to you. Basically, this whole problem shows you all those 5 steps that they're going through. This motion formula, distance equals rate times time, or really rate is distance divided by time, is from the original, is used a lot, so that's why they bring that up again. Here they show it in table form, which they're going to use to derive what's the methodology we should go through. And these get a little more complex, especially when we have expressions being written into this algebra. So some more tips, so on. Again, this should be all review. I'm not spending a lot of time going through this stuff, but lots of word problems in this section. And they go through a lot of stuff to do that. Inequalities. We talked about equations. That's when things are equal. Well, with inequalities, we have this inequality symbol and so on. You know, where do you think they got this symbol from? Here is a less than symbol, and this is true. -3 is less than 5. Well, it comes from the number line. This means -3 is left of, on a number line, 5. This is from the end of the left hand side of the number line has an arrow, right? that points to the left. And so that's all that means. Negative 3 is left of 5 on a number line. If it was reversed, if I had 5 is right of, points to the right of negative 3 on a number line, and so on. I think that's a lot better than all that alligator eats the bigger one and all that kind of stuff. Is think about what it actually comes from and deal with that. Now, inequalities, solutions to inequalities make the inequalities true. So that's what they're talking about, truth. But there's a lot of times there's an infinity of values that will make that inequality true. So we have set issues. That's why we have sets, to deal with things we can't specify with by writing down a certain number or multiple numbers. So the solution might be an infinity, which we'll do puts us back into set notation. Here's our number line, and if I look at this one, it says x is less than 2, or all values of x that are possible to make this true are left of 2 on a number line. That's a handy way to do that. If I look at this, that's what this red area here is trying to draw a picture of, this infinity of solutions, or an infinity of x values that make this true, this inequality true. Now, the format, or the way we use this for rules to graph, is we highlight the part of the number line and then if it continues on, we highlight the arrow saying, hey, it keeps going to the left forever. And this curved line here at the 2 means that it does not include 2, compared to this next one where y is right of or equal to. If I was going to graph something equal on a number line, it means if I say 3 is equal to 3, it means that, or better than that would be like saying 3 is equal to 6 halves. On that number line, the dot that we'd put on the number line would just lay over each other. They're exactly in the same position. That's what equal means. Well, here we say y is all values of y, or things that I put in for y that will make this true, are right of or right on negative 3. So here's that picture. Now when we include negative 3 at our border here, it's a square bracket instead of this curved bracket, means it includes that negative 3. And then they're talking about some stuff. And now they get into defining what we were seeing in those pictures, set builder notation and interval notation. Here's set builder notation, and how this reads is the set of x such that x is less than 3, or all values for x such that the values for x are left of 3 on a number line, if I want to interpret that a different way as far as trying to get a visual of what that means. But that set builder notation we're going to use a lot. And then this interval notation is something new. It's new to me in this book, but it use curved lines if it doesn't include that. So if we have things that have like a section in our number line rather than a ray basically going on from one direction, we define the endpoints basically, and then if they're included, they have the square brackets. Like in this case, this is A is all values left of x, and x is left of or equal to B right here, okay? And this case it'd be square bracketed, and in this case the curved bracket on the A side and the square bracket because of the equal sign, so on. Take a good look at that and you'll see the pictures, and here's the 3 different ways we can represent solutions to inequalities. Now, solving inequalities using the addition principle are just like equations, and that's what they show us. The only thing different about inequalities you have to watch out for is when you multiply, this multiplication principle. If you multiply by a negative, you got a problem. it does do something to the inequality symbols. So, like if I have 3 is less than 7, or 3 is left of 7 on a number line, is that true? Yeah, that's a true inequality. Well, if I multiply both sides by a positive number, a positive 2, I still end up with a true or equivalent inequality. The 6 is less than 14. But if I multiply by a negative number, if I multiply by negative 2, I end up with negative 6 and negative 14. Well, is negative 6 less than negative 14? Or, in other words, I still like doing this, especially when we get into negatives. Is negative 6 left of negative 14 on the number line? No, that's not true. So when we multiply or divide by a negative, we have to reverse the inequality symbol, and that's what they're doing here. Okay. Go through the examples. Here's some animation to explain that. Then they're going to have a kind of summary, connect the concepts that we've gone through. And there's our problems. And then they get into solving applications with inequalities. A lot of language on interpreting. I would recommend that you go through all of this. Okay? Translate at least and at most. They really mean something other than equal. Okay? And it goes through that. And I think that's pretty much a chapter. Other than they might go into some applications here at the end of this thing. No. So that's chapter 2. Very good resource thing here. Talks about consecutive integers. A lot of things that are useful stuff for translating. And they got some other activities here. And then these study summaries are really good. In fact, before you take the quizzes on these chapters, I recommend that you go to the end of the chapter to the study summary. It goes through every section, probably a little more detail in some cases than I actually did here. So good luck with chapter 2, and talk to you soon.